All right. The other mechanism that we're going to study as far as alkene reactions go is called the three-membered ring. And just like the carbocation pathway, we have two distinct types of reactions that we'll see using the three-membered ring. The first one is halogenation. And I've got the overall reaction set up here. We start with an alkene, and we're going to react it with some kind of halogen. And halogens are always, when they're monatomic, they're always going to bond to themselves. Remember that. So we could have chlorine, bromine, or iodine. Once again, fluorine won't work, too electronegative. But when I get products, I'm going to get two distinct stereospecific products. Both are going to be in the anti-configuration. So one of them will be forward, the other will be backwards, or the other way around. I cannot have both forward or both backwards. That will not happen. So I only get anti-products here. Because my halogenation is going to occur with both of them being the same element, Markovnikov rule does not really apply here. Because, I mean, which one is going to attack the more substituted carbon? Well, they're the same thing, so it doesn't matter. So let's go ahead, let's rewrite this and take a look at the mechanism that is occurring here. So I've got the mechanism set up here. I'm going to have my pi bond on this alkene attacking one of the chlorines. Once that attack occurs, the chlorine is going to give up its bond with the other chlorine, forming an anion. After that attack, we've got something a little bit different. We have our chlorine bonded to both carbons at once, which is able to happen due to chlorine's especially large electron cloud. The same thing is going to be true of bromine and technically iodine. So, chlorine here is going to hold a formal positive charge. That positive charge happens because chlorine is sharing both of it's sharing both of these carbons. That does not mean that the carbons have a negative charge. They are neutral. So the formal charge on chlorine is positive. You could go ahead and calculate this if you would like. The formal charge on both carbons is still going to be 0. On top of this, this chlorine, which in this case is called a chloronium ion, is going to be more electronegative than these carbons. And so it's going to pull the electrons in those two bonds closer to it. And so even though we have a formal positive charge on this chlorine, we're going to end up with a dipole across these two bonds, resulting in a partial positive charge on each carbon and a partial negative charge up here, kind of in the space of that three-membered ring. That's a way you can think about that. That the chlorine is going to be positive, both carbons are going to be positive, and the negativity balancing that out is going to be inside of the three-membered ring. So the negativity is housed in the three-membered ring, and this chloride anion is now going to be attracted to these two carbons. If we have one carbon being more substituted, it will be better at retaining a positive charge, which means it will be more positive, and the chlorine is going to be attracted to that one especially. But in this case, it's not really going to matter, because either way I'm going to have a chlorine on one side or the other. So, when the chlorine attacks, it has to attack from the side that the other chlorine is not. The chloride has to attack from the back side here, because the chlorine is sticking out this way. So it's going to be attacking one of these carbons. When it does that, it is going to form on the opposite side of its partner chlorine. And thus we get our final product. It is going to have an anti-configuration. Now it's pretty irrelevant in this case which carbon this chlorine attacked, and it's equally irrelevant whether this initial chlorine got attacked in the front or in the back. So we have a mixture of stereochemistry. But the one thing that is important is that when this chlorine attacks, it has to attack the opposite side from this chloronium ion. And so when that happens, these chlorines have to be facing opposite directions. So it's got to be in opposite directions. So we're only going to get anti-configurations here. So in halogenation, we go through a three-membered ring and result in anti-products. Let's look at our other reaction running along the three-membered ring mechanism. In this mechanism, we're going to be having a halogen reacting with an alkene in a water solution. Water will be acting as our solvent, which will help to stabilize the anion after our three-membered ring step. When that occurs, the water is going to be able to attach instead of the other halogen. So we're going to get a mixture of products once again that is going to be in the anti-configuration. So this is going to be stereoselective to the anti-configuration. No syn products, only anti. And we are going to get Markovnikov addition. So we are going to be regio-specific here. That means that our oxygen, our alcohol group, our hydroxyl group, is going to be attacking the higher substituted carbon. And we're going to see what that looks like in just a little bit. So let's go ahead and erase this and draw out the mechanism from start to finish to see how this is working. So we're all prepped with our cyclohexene. This double bond is going to be attacking one of these bromines. And I'm just going to have it attack the closest one. That bromine is going to give up its bond with the other bromine. So now, due to the presence of the water, the H2O, this bromide anion is going to be stabilized through hydrogen binding. It's going to just act as a dissolved anion, just like any other dissolved salt would. Another water molecule over here, however, is going to be attracted to the area of a little less electropositivity on these carbons. So this bromide is once again going to have a positive formal charge, and we're going to have a partial positive charge on both of our carbons, with a partial negative charge in between our three-membered ring. Now, which of these carbons is this oxygen going to attack? Well, I'm so glad you asked. This partial positive charge is going to be easier to hold on to by that carbon because it also has this methyl group sticking up right here. Notice, the bromine is sticking out of the page. It is held forward, and there was an initial methyl group on our cyclohexene. This methyl group is now sticking backwards into the board and is helping to stabilize this partial positive charge. It is going to be more positive than this one. So this oxygen right here, which is more electronegative, is going to be attracted to this greater area of positive charge. That's why this is going to be a Markovnikov addition. So this oxygen is going to attack this carbon. Now, when this oxygen attacked that carbon, it has to attack from the opposite side of the bromine. It's going to be doing this underneath that methyl group. So when we get our final product, we need to make sure that we have it in the anti-configuration. That is going to be extremely important in the three-membered ring. The bromine and the resulting water molecule have to be in opposite configurations. Doesn't matter which one's forward, doesn't matter which one's backwards, but one of them is forward, the other one is backwards. Either way. So, once we have this point, once again, the water molecule itself is not exactly a stable functional group. And so another water molecule is going to come along, attach away a hydrogen, and we're going to be left with an alcohol. So now we've got our final product. Keeping in mind, we've got our bromine facing forward, our alcohol facing backwards, and we still have our methyl group, which is now forced to face forwards. So, what are some of the things that we need to keep in mind when we're looking at the three-membered ring mechanism? So in the three-membered ring mechanism, we are going to have some stereoselectivity, which means that we're going to only have the anti-configuration for our products. So we need to keep that in mind. Whenever we do the three-membered ring, we do need to show the stereochemistry of the products. We will have regiospecificity when we're doing halohydrin formation, because we're going to have two distinct functional groups. Our second functional group is going to be attacking the more highly substituted carbon. If both are the same, it makes no difference, and we will end up with a mixture of products. So we will have Markovnikov's rule applying wherever it is able to. Finally, we will not have any carbocation, so we will not have any hydride shifts. So we won't have any shifting of any kind, but we do need to keep in mind that three-membered ring mechanism. As a final note, we had a page that we were looking at that had 12 of the must-know alkene reactions. A lot of these are going to operate in a very similar mechanism. Using the carbocation and the three-membered ring mechanisms, we could investigate a few more reactions. For the sake of brevity, we will not. But you should keep in mind that of the 12 main alkene reactions, most of them operate according to one of these two pathways. And there is only one other mechanism that we would need to investigate if we wanted to look at all of them. However, that gets a little more complex and is beyond the scope of this class. But you should keep these in mind as you're going into college-level organic chemistry, because these same pathways will help you even with more complex reactants.